I'm glad you read it because I have a hard time reading that too. So we're looking at whether energetic charged particles can create molecular hydrogen. And so all my collaborators are on the LRO crater team. That's the Cosmic Ray Telescope for the Effects of Radiation. And all of us except for Tim Stubbs are at the University of New Hampshire. We'll start back in October of 2009 with the LCROSS Impact. And the upper stage of the Centaur rocket created an impact plume. And a couple studies came out within the past few years showing that the water by mass in the regolith in that area in Cabeus crater was about 5 to 6%. And then the LAMP team, and then later on Hurley did some more work on it, showed that the molecular hydrogen by mass in the regolith is about 0.05%. So that means that H2 molecules count for about 8% of all H2 and H2O molecules. So I'm showing here a value that's relating the molecule numbers, not the mass numbers. So 8% of the molecules are H2. So the question is, can energetic particles create the observed H2? Energetic charged particles like cosmic rays and solar energetic particles can penetrate permanently shadowed regions, and they can drive subsurface chemistry. Cosmic rays can go down, penetrate almost to a meter below the surface, and solar energetic particles usually no more than a centimeter or so. So they can affect water ice that would otherwise be difficult to get to. There are two ways to do this, two chemical pathways. One of them is for the energetic particle to dissociate a water molecule into O and H2. And this is definitely an unlikely process, but it can happen. Something that's more likely is for two water molecules to be dissociated, resulting in two hydroxyls, and then the free hydrogen atoms can combine and form H2, and this is definitely a more likely process. Regardless, it doesn't matter exactly which process is the predominant one, even though the one on the right seems to be. It doesn't affect the final values too much. So to estimate the amount of molecular hydrogen formed by radiolysis, we created a model with three main components. And the first component is the radiation dose penetrating the regolith containing the water ice. To measure the radiation dose rate, we used CRATER, the Cosmic Ray Telescope on LRO. And that's an image of it right after it was integrated into the spacecraft down at Goddard. Nathan Schwadron et al. Showed last year that the GCR dose rate over the history of the mission was about 0.02 electron volts per molecule per million years. And other studies have shown that the cosmic ray flux probably hasn't changed all that much over the history of the solar system, or at least over the history of that we're looking at the past couple billion years. Now this plot that I'm showing in the background shows the accumulated dose over 3 years of the LRO mission. And the accumulated dose is in units of centigrade, and a gray is equivalent to 1 joule of radiation being deposited in 1 kilogram of material. So CRATER's been measuring that faithfully over those 3 years, and you can see a steady increase for the first couple of years, and then a few bumps starting in January of 2011, or a little after that, and then some pretty sharp increases starting in 2012. And each of the little bumps and big bumps that you see is a solar energetic particle event. Those are much more sporadic, and they, if I were to show you a time series, you'd see a smooth variation of the galactic cosmic rays and then sharp spikes of solar energetic particle events on top of that. And most of the radiation dose that Crater measures is actually from the SEPs. You can see it's about an order of magnitude greater than the GCR radiation dose. That's the first component of the model. The second component of the model is meteoritic mixing or gardening of the regolith. And this mixing affects the exposure time of the regolith and hence any water ice that's mixed into the regolith. So I'm just going to walk you through a cartoon that shows how this works. So here's a cross-section of the lunar regolith, and we know that the SEP particles that Crater observes or detects penetrate to about 2 millimeters below the surface. So that's the EP1. And we get this value from the National Institute of Standards lookup tables for how energetic particles penetrate in a variety of materials. And here we're using silicon dioxide as a proxy for the lunar regolith. And actually the energies we're considering, the exact material that you use doesn't have much of an effect on the penetration depth. So 2 millimeters is pretty good. This is not to scale. The GCRs penetrate down to about 36 centimeters. So much deeper than the SEPs. Now we're going to go from a static cartoon into basically a time series where time increases to the right-hand side. And the gardening depth increases with time. So Arnold, back in 1975, did some Monte Carlo simulations of how meteorites will mix together the lunar regolith, both horizontally and vertically. Right now I'm just showing vertical mixing. So everything above that orange line has been thoroughly mixed. So what this does is it divides time into 3 regimes. The first regime is one in which gardening has no effect on the exposure time of the regolith. So when I'm talking about exposure time, I'm talking about material that has been gardened. How long has it been exposed for? So if the gardening depth is more shallow than the penetration depth of both the SCPs and the GCRs, the exposure time just increases linearly with time. If, however, the gardening depth is deeper than the SCP depth, but shallower than the GCR depth, then meteoritic gardening affects how long the material has been exposed to SCPs. So it takes about 1 million years to garden 2 millimeters, give or take a few million years, to garden 2 millimeters of regolith. So what happens is after that time, then material that has been exposed to SCPs has been thoroughly mixed down to depths deeper than the SCPs can penetrate. And so you can actually have more regolith being exposed to the SCPs. And then the same thing happens once the gardening depth becomes deeper than the GCR depth. And that transition occurs at about 400 million years. So what we're doing in this is we're assuming that each layer in that gardening region contains grains that have spent time at any given depth above the gardening depth. So that means that all the layers within that garden zone have the same average maturity. So although the exposure time of the material above the gardening depth is described by this equation. So the exposure time linearly increases with time if the gardening depth is less than the penetration of the energetic particles. If the gardening depth is greater than or deeper than the penetration depth of the energetic particles, then the exposure time is adjusted by the ratio of the penetration depth to the gardening depth. That's the second component. The third and final component is the chemistry that's going on, so the radiolysis. And I forgot to mention at the beginning, we are only considering water that's been there for a long time, so water that's been deposited by cometary impacts. So this is the equation that describes how many H2 molecules form with respect to the original number of irradiated water molecules. So G is just the G value. That's the number of chemical reactions that result in H2 per 100 EV deposited per H2O molecule. That value probably lies somewhere between 0.1 and 0.7. This is based on work by Hart and Platzman back in the 1960s.
Yeah, Andrew, you have 90 seconds.
Yes. Thank you. So 0.1 is the value that it would be for if the energetic particles were just protons. 0.7 is if they were all alphas, given that about half the radiation dose from cosmic rays is due to heavier alphas and heavier ions. It's likely that the G value is closer to 0.7. D is just the radiation dose rate. Tau is the exposure time. So you put all the components together, and this is what we get. So what I'm showing here is the range of molecular hydrogen that can form. The lower x-axis shows the time since the irradiation began, or since the ice was deposited. The upper x-axis shows the gardening depth associated with those times. And then the y-axis is showing how much molecular hydrogen is formed with respect to the original amount of water molecules. And so the lower line shows what happens if G is equal to 0.1, and the upper curve shows G equals to 0.7. And that knee that you see there, right around 35 centimeters gardening depth, divides the regimes from where the gardening depth is less than the GCR penetration depth and from where it's greater than the GCR penetration depth. So if you remember back all the way at slide 1, the amount of H2 with respect to the current number of water molecules is about 8%. And so here I'm showing it with respect to the original number of water molecules. And we'll be doing some more work to figure out what other processes can destroy water molecules. So this, so if you do that, it actually shifts the values up. And so I'll just get to the conclusion slide. It seems like GCRs and SCPs can account for between 10% and 100% of the observed H2. So 10% of G is closer to 0.1. If G is closer to 0.7, then we can account for all the H2 that's been observed. And it's something that I didn't show in this, but GCRs are responsible for the lion's share of the radiolysis. SCPs, even though their dose rate is much higher than the cosmic rays because of their shallow penetration depth, GCRs are actually more important than the SCPs. And then the paper that goes into more detail about this is just released, is in press right now in the past couple weeks, so there's the reference there if you want to look it up. That's it.
All right, very good. All right, that's congratulations on the paper, Andrew. That's great. We're entertaining questions right now. I see someone is typing. Andrew, I have a quick question in the meantime. How easy would it be to move this model over away from the polar region into the sort of the mid-latitude or lower latitude regions, or say mid-latitudes where you might have a sort of this OH buildup in the SiO2?
I think that would be fairly straightforward. Right now, the chemistry is really simple in this, but I can definitely change that around to account for that.
All right, because I mean, it looks like you'd be splitting more like SiO2s and that kind of thing.
Yeah. Right now, I'm just focused on the H2O. I don't have any of the SiO2s in there.
Yeah, interesting. Okay, here we go. If consider the absorbed H2 that is re-released, how much does it change the estimate? What is the contribution from cosmic ray-produced H2?
That we haven't looked at all. So yeah, and I glossed over to loss mechanisms for the H2. But we haven't looked at adsorbed H2 at all. So.
Okay. I might suggest while we're waiting for one last question. Yeah, good. Andrew jumped on. Good. So one other question. Let's see. Well, maybe that's it. Oh wait, here we go.
False alarm.
Yeah. Oh, here we go. This model is correct if the surface has not been disturbed for a long period of time, right?
Other than the meteoritic gardening, yeah.
And that's a pretty big disturbance.
Yeah, it is a pretty big disturbance.
That's not trivial. All right, I think we are